All right. Hey, thanks, Freddie and Avi. Shalom. Greetings, everybody. It's an honor to speak here. I'll be talking about chiplets. I'll be talking about Universal Chiplet Interconnect Express, UCIe. I know it's a mouthful, but UCIe for short. It's an open interconnect standard for doing innovations on package using chiplets. Here is the agenda for today. I'll talk very briefly on some of the mega trends in the computer landscape, talk about interconnects, which is an important pillar. Where does the die-to-die interconnect like UCI fit in there? Then we are going to delve deeper into UCIe and spend a little bit of time on future directions and conclusions. So bulk of my talk will be on the third bullet here. So we see some mega trends emerge in today's computer landscape. AI is the new frontier. Cloud computing is everywhere. Networking and edge, they're exploding also. They're increasingly using the cloud infrastructure. So these are the trends that are driving the demand for faster and heterogeneous data processing. We need a lot of memory bandwidth. We need a lot of IO bandwidth. We are in this virtuous cycle here. Better computing infrastructure means we enable new applications. New applications in turn require even more capability from the compute infrastructure. So that cycle, virtuous cycle, continues. And interconnect is at the center of all the data movement. And it's one of those important pillars in the compute landscape. Now, here is my taxonomy of the different interconnects, as you can see in the picture here. And I would broadly categorize the wired interconnect world into two categories: latency tolerant, the networking type, and latency sensitive, which is the load store interconnect. And the fundamental reasons are from the scale in which they are deployed. And it results in some very key differences in their characteristics. Networking needs to scale to hundreds of thousands of nodes in a data center level. So they are narrow, they tend to lead the speed transitions. Latency cost, those are secondary in those considerations. Now, in contrast, if you look into the broad class of this load store interconnect, those are primarily at the board level, or as we will see at the package and chiplet level. And they need to scale to hundreds of lanes. They are also, because those are coming out of individual SOCs, those are too many lanes there. Power is important, of course. Cost is important. Area is important. Latency, of course, is very critical. And most importantly, they need to scale. Now, on-package interconnect, which is the one that you see here, that's also in the predominantly in the load store category, which is these are got the ones that have got the architectural ordering semantics, things like your memory access semantics, cache coherency, or PCI Express style load store interconnect. These are the ones on package that we will see they need to scale to tens or hundreds of thousands of lanes. So now it's even more important to get even lower power, lower area, lower latency than external on the board, and soon moving to the rack level interconnects like PCI Express, CXL, or SMP cache coherency protocols like, for example, Intel's QPI or UPI link. Now, the industry has rallied behind this UCIe as the standard interconnect, the same way the industry has rallied behind PCI Express and CXL at the board and the rack level as the interconnect. So now let's talk about UCIe. There are 4 guiding principles that we follow in UCIe, and several of us, we have decades of experience in driving very successful industry standards like PCI Express, CXL, USB. So those are, first of all, you need to have an open ecosystem. Things need to be plug and play, right? You need to be able to plug anybody's component in any system and it should work. Otherwise, it's not really an open ecosystem. The evolution of the technology needs to be in a backwards compatible manner, because not everybody is making the technology transitions at the same time. You don't want people to force the technology transition. They basically make the change in their underlying technology whenever there is a need for them, inherent need for them. You also want to have the best power, performance, and cost metrics across all the segments, right? This is where the quantitatively you need to deliver what people need. And then, of course, you need to continuously innovate, because one thing we know that the compute landscape is not stationary, it changes very rapidly, right? And we need to be able to make sure that we are staying in tune with the demands of the compute landscape. So these are the 4 guiding principles that we have seen, and we live by in those other successful standards. And when we started UCIe, those were the same 4 guiding principles. UCI is an open industry consortium. We have more than 135 member companies across the globe. And as you can see, these companies are the who's who in the field of semiconductors, in the field of foundry, IP, packaging, cloud service, you name it, right? They are, and then there are 12 board member companies that are represented here currently. Let's start with first, what are chiplets and all of that. But before I start, I would, people are very familiar with Gordon Moore and Gordon Moore's Moore's law, and this came from his seminal paper, which is the cramming more components onto integrated circuits, which was published in 1965. And in that paper, Moore postulated what is known as Moore's law, right? And it has basically says the number of transistors double every 2 years. And that keeps going strong. But in that same paper, Moore also had predicted the day of reckoning, where he said that it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. And that day of reckoning is already here. If we look into the mainstream commercial offerings, whether it is CPUs, GPUs, whether it is memory, it's multiple components, multiple chiplets that are packaged together. Oops, moved a little bit too fast. Okay. Now, there are many drivers for the on-package chiplets. As the die size increases in order to meet the growing performance demands, right? As I said, we are in this midst of, insatiable demand for performance, memory bandwidth, storage, all of those. Designs are running up against the die reticle limit. And, examples are multi-core CPUs, GPUs, those are in the volume market. The other challenge is the yield challenges. Larger dies, of course, they yield less. Smaller dies yield better. Third motivation is on-package memory. We need to deliver the memory bandwidth in order to feed the computing beast that we have. And more and more people are incorporating memory on package in order to deliver that bandwidth. And then there are other emerging drivers in this landscape. IP porting costs are through the roof. There was a study done by IEEE, HIR, which showed that even if you didn't change anything in the IP, just the fact of porting the cost, they look into different aspects like software, hardware porting, validation costs, and all of that. It's a hockey stick, right? It goes up with the more advanced process node. It would help a lot if we could do chiplets where your functions that are not changing are in an older chiplet, and you can integrate that, and only the functions that are changing, you put that in a new chiplet. Now, related to that cost factor is also that, if you look into that more advanced nodes, it's much more expensive. And again, those functions that can really benefit from the most advanced nodes, you want them to be in the most advanced process technology. And then there are others that can be in the older process node where you're reusing your dies. So things like your memory controller, IO controller, those can be in a more mature process node and can be reused because those do not change as frequently. And then, of course, chiplets, they offer the time to market advantages because you're reusing chiplets that have been proven. You can also offer bespoke or customized solutions. You can envision having a mix and match of compute cores, different number of compute cores, memories, acceleration functions, IO, as shown over here. So we need to think of the package as an open innovation slot, similar to PCI Express or CXL at the board level. And what we really needed at that time, this was back in 2022, was an open industry standard like PCI Express and CXL at the package level. And UCI is basically that standard, and we have rallied the whole industry behind. And our vision is one of mix and match chiplets, right? You have got these heterogeneous integration of chiplets where you got a C of course in multiple chiplets, you got acceleration functions, you got some customized IPs, you got analog functions, you got memory, all of them packaged together on one package. So that way, what we also want is to revolutionize the field of computing at the package level, similar to what we have done at the platform level. So the way I would summarize this is package is the new platform for innovation, and package is also the new SoC. So that's the way to think about it. So now let's look a little bit on what UCIe is. There are two generations of UCIe, UCIe 1.0, 1.1, and then I'll talk later about UCIe 2.0, the second generation. UCIe 1.0 was donated by Intel. We started the consortium in 2022 March. At that time, we had also the UCIe 1.0 specification. UCIe 1.1 is an enhancement to 1.0. It's fully backward compatible, and the enhancements in 1.1 were few engineering change notifications for things like automotive usage. We did a few optimizations around the area of the bump map, compliance testing kind of optimization, and the interconnect in 1.0 and 1.1 is planar interconnect, 2D, 2.5D. Both 1.0 and 1.1 these are fully defined specifications. They use a layered approach as shown here. And the idea is that different layers can be implemented by different people and they will be interoperable. And they're also, of course, interoperable with other chiplets that implement UCIe. Now, it's critical to have this holistic approach where the layers are separated and they are also fully defined for successful interoperability. For example, the physical layer, it includes things like clocking, analog, sideband, scrambling, descrambling, link training, lane repair, lane reversal, all of those, the entire domain of bump map, all of those. Die-to-die adapter, it handles reliable delivery of bits across the link. It has things like CRC, retry. It can support multiple protocols. And then the protocol layer can be PCI Express, CXL, or it can be any streaming protocol. Things like people do AXI, CHAI. We have our own flavor of symmetric multiprocessing that we deploy inside the package. So those, we also have raw mode if you just want to use it as a bit stream. So why did we natively define the mapping of PCI Express and CXL? Well, these are as I told you, these are the ubiquitous standards. SoC construction issues are addressed with PCI Express CXL. Fundamentally, that's deployed widely in the board level. People know how to make things work, with the clock and power, right? Things like software device discovery, error reporting, all of these things are taken care of. Those things exist. From a usage model point of view, IO attach you can do with PCI Express or CXL.io. Memory use cases, CXL.mem. Accelerator use cases, CXL cache, CXL mem, and of course the IO aspect. And streaming protocols, these are similar to like our SMP cache coherency protocols that are running on PCIe. So we also wanted to make sure that those streaming protocols ran on the UCIe infrastructure. We define configuration registers at each level, form factor, we define manageability, security, compliance. These are all essential ingredients to make a fully successful interoperable ecosystem. The picture here shows UCIe 1.0 and 1.1, the planar interconnect. So this is known as 2D, the picture on the top left. The pictures on the right are 2.5D. You will use 2D for cost-effective systems, which go for a longer distance, up to 25 millimeter. The bump pitch is 100 to 130 micron on this side. Advanced package, which with 2.5D, it's for power efficient performance. You pack a lot of bandwidth, very high density, and we support any kind of packaging. There are multiple technologies available. I've given 3 examples here. This is Intel's EMIB. This is TSMC's Covers. This is ASC's Focus. There are solutions from Samsung, and actually, same company has multiple different solutions also. And the same dies that you can manufacture here can be manufactured anywhere, and they can be packaged anywhere. That's the beauty of it, similar to what you do at a board level with things like PCI Express. And it offers the SIP designer, system in package designer, the flexibility to pick and choose which dies to use and which packaging technology to deploy for the type of application that they have. Compliance, it's one of the key criteria for any successful standard. Pretty much almost all the successful standards, multi-generational standards, they have a compliance program. And the slide here shows how we do compliance with both standard package as well as advanced packages. We have the notion of a reference known good package and a golden die, which is known to work and also has certain testing characteristics. And you can use that to test a device under test, right? This is standard package, and the one here is the advanced package. And you can control this through an external interconnect, like through an FPGA, by using a laptop. That will be the setup. And people bring their device under test, and you test for different aspects of it, right? You have all these reference channels, you have characterized them, so you can do a wide range of tests. So the ingredients at a deeper level are, for example, there are 3 sets, 5 for the 5 testing, die-to-die adapter for effectively the die-to-die level of testing, and then the protocol compliance. So, functions that you want to test are timing margin, voltage margin if appropriate, bit error rate, lane to lane skew, things that you test at a physical layer level. The golden die in general will have all the capabilities, but it also has some additional capability, like it can inject errors, it can cause timeouts, right? And that way you want to test the error cases. We expect errors to be, as you will see later, you'll hardly see errors because these are very well defined channels, but when you're testing it, you want to make sure that you're able to inject the errors, and that's what the golden dies have. We have defined error injection capability. Die-to-die compliance will be things like replay, no-up, test plate, all of those kind of things. And again, golden die supports all the formats, is able to do error injection. For protocol compliance, we expect the FPGA or whatever is the means to download the, let's say if you want to test with PCIe protocol or CXL protocol, just download those through into the golden die and then exercise those protocols and just use the underlying protocols compliance mechanism. Now, UCI's usage model is construction of an SoC or a SIP at a package level, right, in order to bring the system from the board into the package level. In the picture here, you can see that you got processing elements. Most likely those will be in the advanced node. You're going to have GPUs or accelerators. Those could be in the most advanced nodes or a mix of advanced or established node, depending on what type of acceleration functions that you have. You will have memory and IO controller. You're going to have memory here. They're all connected through UCIe. And then, of course, you're going to have your external interconnect, whether it is PCIe, CXL, whether it is USB, 224 gig, or what have you, right? All of those things. And they're all going to be connected using UCIe as the underlying interconnect. And we expect UCIe is designed to cover the entire compute continuum, from handheld to client to workstation, server, you name it, right? So just like PCI Express, the same standard goes across all the usage models. We want, the target for UCIe is to cover all the usage model here. The second type of usage model is around UCI-based read timers, and this is a novel concept which we introduced with UCI 1.0, and it helps with basically off-package communication. For example, think of co-packaged optics. So you can see here that this is a CPU package. We have all the ingredients here of the CPU, multiple dies. We put a retimer here, and then we escape the package using an optical connection. And the protocol might be, for example, CXL. And we can go to the top of the rack, some kind of a switch, or we can go to another place where there is a pool of memory, there is a pool of storage, maybe there is a pool of accelerators that we want to use. You have the retimers on the other side. there is a in this example there is a CXL switching die. Multiple dies are stitched together on this package and connected through optical, and then you have an access to a pool of memory, a pool of storage, a pool of acceleration. So now what you have is that you have this vision of disaggregated resources at a rack level or even at a pod level, where you got compute, you got different type of acceleration functions, you got memory, you got storage. They're all connected through the off package UCI based retimers, and then you can basically you can while running a task, you can say, hey, I need more memory. You can go to this particular place and get some from the pooled memory. Or you got a bunch of servers that want to communicate with each other, so that you are trying to collaboratively solve a problem. You can even use shared memory using load store semantics. So that's the thing that UCI enables through this retimer based approach. Now, so UCI 1.0 and 1.1, those have been really good in terms of, and we'll see some examples of people deploying, some test chips and everything else in a few slides here. But there are still many challenging problems that we need to solve if we want to realize the vision of an open plug and play chiplet based ecosystem in a much broader scale. And we have done that with the recent UCI 2.0 specification, again, which is backward compatible with the prior generation. It builds on top of these. Testability, manageability, debug. These are three main aspects, and we expect this to see continuous innovation. Now, we already had several hooks in 1.0 and 1.1 specification to address this at the interconnect level, right? So things like loopback, margining, fault reporting, sideband, all of these were there from the beginning. But there are things at the chiplet or package level that we felt that we need to take a holistic approach of looking at things beyond the interconnect, right? And then work with whatever else kind of technologies that people might have. So we decided to look at this again holistically, from the die level at SOT to package level at bond to the field level deployment, basically the entire silicon life cycle with feedback in order to improve things upstream. So let me give an example. At a test level, you can probe the bumps, right? You can probe them with a tester. You cannot probe the micro bumps, especially as the bump pitches go down, because the bump pitches become narrow. So your probe is not enough it is not good. It doesn't have the resolution to land precisely at with the smaller micro bumps. And moreover, even if you could land it, it's going to destroy some of those micro bumps. So we decided that we should use those other bumps that exist, and there is plenty of them. Every chip has got multiple sets of bumps, so we could use some of them. And as you can see over here, some of the chiplets, for example, that will, once you package them together, how do we test them? Some of them may not even have package pane accessibility. How do you debug something once you have assembled it together? You cannot put, for example, a scope here or a logic analyzer here, because those are packaged, right? How do you handle manageability? How do you do field upgrades? How do you, download firmware upgrades, for example? How do you do all of these things securely, right? And as I said, some of these chiplets, again, may not have a direct package pin access. For example, chiplet 9, 8, or 4 here, those do not have a direct package pin. And for these functionality, testability, manageability, debug, different chiplets have a wide range of bandwidth demands, right? For example, how much scan chain bandwidth do you need? Well, it depends on how big of a chiplet you have, right? How much debug bandwidth you need? Well, again, depends on how complicated functionality you are implementing, right? How do you debug this and during runtime? Do you and of course it becomes, like I said, it becomes more harder if the chiplet doesn't have a direct package pins. Do you deploy should we come up with a solution that we use the existing UCI mainstream functionality pins, or should we just have a separate set of pins for this set? Again, the answers will be different for different set of people. And again, what we did was we said that people will have different sets of needs. We just need to enable them. So what we have done with UCI 2.0 is we have defined a common infrastructure that will use the current IP building blocks as well as external interfaces at the package level. And this will include like bridging to these external interfaces. Like, for example, you want to test something, you want to come through an SM bus, you need to have a SM bus to a UCI bridge, or you want to control something, right? And from there, you go to the other chiplet using UCIe, because the other chiplet, for example, over here, doesn't have any external connectivity. So we have defined all of those things with UCIe 2.0. And again, these are not UCI specific things, but we need them so that the once you put things together, they can work seamlessly. That's what we have done. So effectively, the key takeaway here is that 2.0 introduces a common UCI test debug management infrastructure that can work through these multiple aspects across the silicon lifecycle. So let's delve a little bit deeper into it. So I'll give an example of the UCI DFX architecture, and it comprehends things like test, debug, telemetry, all of those, and it's covered through what we call the management fabric. That's common and that we have defined. And this is a hub and spoke model within each chiplet. DMH stands for DFX Management Hub, and DMS stands for spoke. So that is, each chiplet has at least one hub controlling one or multiple spokes. The hub basically provides for discovering the capabilities and routing of management transport packets that are related to these test debug things that are coming into each of these spokes within the chiplet. And if appropriate, you forward them to across to the other chiplet if that's where the packets are destined for. Spokes are basically entities that implement a given test, debug, or telemetry functionality. So for example, your membist, it's a spoke, right? We are not asking you to do a particular type of membist engine or a particular IP. Whatever you have, what we will define is a wrapper that's going to access that membist so that you can go ahead and access it from any of these external package pins using the UCI 2.2 infrastructure. Same thing with the debug. And for example, your debug engine can be spoke in the and again, these are your existing IPs. No need to make any change. All that we are doing is provide for how to address them, how to go and access them. So what we have done is you have defined architected registers, things like header and all, effectively a wrapper around that you can put using UCIe, and also a set of packetizers and that can go across UCIe. And from a system level usage point of view, basically think of it as, you got your vendor specific drivers. This is similar in concept to that of, for example, when you have a particular company access storage controller, how does OS know how to deal with it? Well, there is a well-defined device driver that particular controller provides. OS knows how to talk to it through calling that device driver. This is similar. You have your, for example, pick your favorite IP vendor. You have their membist engine deployed here. You have some wrapper saying this is from a UCIe point of view, this is the vendor ID of the vendor that provided with that membist functionality. This is their device ID, which is basically some number that says, hey, this is this particular membist revision ID. Now you know how to access it because they have provided you with saying, oh, you go poke this register, then you poke that register, and so on and so forth. And the right thing will happen at the end. You go back and read these sets of things, right? And again, UCI doesn't need to understand any of this, which registers to go write or read from. You just have provided that infrastructure so that once you figure out that it belongs to this particular vendor, you can then load the thing coming from whichever external system management entity that you're using to connect. So those are the mechanisms that we have. It's a very simple set of things. Use existing infrastructure, just provide with vendor ID, device ID, those registers which are read-only registers, and in any case, all of them have their inherent capability to route things, and then just use that mechanism to route between these different entities. Now, here are some example usages of this UDA. The first one here is an ATE tester. And what it is doing is it is accessing the chiplets multiple scan chains, on the scan controller through using the UCI main band or sideband. Again, these have to be bumps, right? So this is the UCI S kind of thing, standard, because that's where you can put the probe, the ATE probe. The second example here is a ATE tester that you have deployed after you have packaged it. This is at the die level, the first one. This is at the package level where you're testing. And again, this ATE can come and access multiple chiplets and then test the functionality, see if everything is okay or not. This is an example of a debug. You got your remote console, which is a UCI based, USB based. You inject the the right setup, the management packets through the USB using USB protocol. It gets routed internally through the UCIe to the appropriate chiplet that you want to debug, sets up the debug register, and then it also sets up the other stuff. So that way, let's say this chiplet's functionality can travel from here to here to here, and then out it goes on a PCI Express logic analyzers, where you can look into what's going on within that particular chiplet or across multiple chiplets, where you can divide a debug set of bits amongst multiple chiplets, right? So those are the types of things that we enable with UCI 2.0. Now I'm going to switch gear and talk about vertical chiplets. Avi, if there are any quick questions, might be a good time to pause and take them.
No
Okay.
questions so far.
No questions yet. That's fine. Let's keep going then. So 2.0. So again, 2.0 introduced the enhancements towards the debug, test, and visibility functions. It also introduced a new type of connectivity, which is so far 1.0 and 1.1 were planar, 2D, 2.5D. Here we introduced also 3D connectivity and vertical chiplets on top of planar, right? There are a rich set of technology choices that are already available and deployed in the industry. Vertically 3D interconnected chiplets, they have been used by memory device manufacturers, case in point being HBM, high bandwidth memory, for more than a decade now. They have also been deployed in computing devices recently, like for example our own Ponte Vecchio. And one of the recent key trend in this 3D packaging technology is that of hybrid bonding. And the hybrid bonding, the good thing there is that it goes through very aggressive shrinking of the bump pitch between the micro bumps that you have. Those start at 9 micron and down. We see a path all the way to sub-micron level. Now, the advantage of 3D is that basically these are the chiplets that just stack on top of each other. So the interconnect distance is practically zero, right? Remember, 2D was about 25 millimeter, 2.5D was about 2 millimeter. With 3D, it's practically zero between them. So the interconnect distance is practically zero. Now, of course, what it means is that also the interoperability is going to be constrained in the sense that you cannot have something that is 9 micron interoperate with something that is a 1 micron. It has to be, both of them have to be 9 micron and aligned, right? Because you're fusing them together. But even within that constraint, if you look into, as we will see, the key performance metrics that we get out of this integration, it's tremendous. First, we get a huge amount of bandwidth density. We get a twofold benefit here. Reducing the bump pitches, especially if you as they go down, it has got the inverse of the square effect in terms of how many wires are there. And let me give an example. Let's say I do something at 25 micron bump pitch, and then I go down from 25 micron to 5 micron bump pitch. From 25 to 5 micron, I had a 5x reduction in my bump pitch, but my number of wires will go up 25x, right? It's the inverse of the square, right? It's again, what is the distance between them as the distance shrinks? It's a 2D structure, so you can imagine that it goes up as a square, right? So that's the first benefit, that, with 3D, you got hybrid bonding, and those are characterized by very tight bump pitches. Second aspect is also equally important, which is the area itself, right? So far in planar, what happens is that if this is a chiplet, you have to come to the edge of the die. You have to come to the edge of the die and then connect. So basically the periphery of the die, or the soar line is what we call them. That's what you use to generally connect to other chiplets, even on the package or on the board, doesn't matter. But here you can connect them in place. As you can see here in this picture, there are 9 connections, 9 sets of connections. Those are all connected in place, right? You don't have to go to the periphery of the die. You just connect directly, right? So now what you have done is that you have taken a problem that was along the, that was limited by the shore line, and you have increased the area tremendously in which you can do. So those are the twofold increases, right? Bump pitch reduction, and then you didn't have to go to the shore line, right? So as a result, the entire aerial thing is available of the chiplet for connection if you need it. Of course, as you will see later that, the amount of bandwidth you get is tremendous. So it's you're going to have very small amount of connections, but distributed. So again, this picture is with 9 network on chip controllers connecting to another chiplet with, again, 9 network on 9 NOCs is what we call. Now with these, the associated circuitry is very simple, because the key thing is that we need to be bump limited, right? As this bump pitches shrink, my circuit area needs to be small enough so that I fit within the bump pitch. Otherwise, I just do not get any benefit of the shrinkage of the bump pitches. Now, the other benefit that we can get is lower power. Now, once the distance is reduced to 0 practically between the chiplets, you don't have much parasitics there in terms of the capacitance and all of that. Your circuits can be really simple. We can drop down the frequency. We don't have to run them faster. We don't have to do any serialization, deserialization, none of that. We can get, as we will see, an order of magnitude, even lower power. Now, with orders of magnitude improvement in the bandwidth density, area reduction, all of that's possible. So we just need to think of this differently, right, in terms of how we do these aspects. And then that's basically what we have done with UCIe 2.0 3D unidirectional link, forwarded clock, just a simple hardened IP. Eventually, we expect the ESD capacitance to even go away, especially past 3 micron, otherwise we will not fit. And there are techniques available. The industry is working in reducing the ESDs and eventually eliminating them. It's a very simple inverter-based design. And we just don't need to run this link any faster. We can just run them at the chiplet's internal frequency. And that will basically save us in terms of, we don't have to serialize, we don't have to deserialize, we don't have to deskew. We don't need a die-to-die adapter. My bit error rate is low enough that I can just pass signals as if I'm passing them on the die. And basically, you basically have the NOC directly talk to the PHY, which is hardened, and then you just connect to the other side. And again, what is the PHY? It's a very simple inverter-based design. We'll see that. And we don't expect any repair to be done on a lane basis. Let's say there is a repair here. We basically take a subcluster out, use another subcluster. There are enough connections here. There is enough redundancy built in there. You got this. Once you have multiple chiplets, multiple interconnects here, you probably will use a common test, debug, pattern generation, checking logic in each chiplet to control things in order to test the other things. So it becomes like as if you're checking a monolithic die. That's the way to think about it. So,
President, the other question regarding the 3D, both of them are about the power heat dissipation, and people wonder, one question is, what is the effect of 3D on power and heat dissipation? And the other question is how this heat dissipation managed in 3D. So they are completing each other. So can you extend the discussion?
If you don't mind, let me go through I'll talk about the power in a few slides, and I'll try to, if I don't answer the question, I'll get there.
Okay, thanks.
Yeah. So this is like again showing the circuit here for the UCIe 1.0, 1.1, which is 2D, 2.5D. For the standard ones has got a few extra components because it goes the 25 millimeter distance. The advanced one has got less components. But by the time you come here to 3D, again, my max frequency is 4 gig, which is basically what the SOC frequency is. I don't need any of this serialization, deserialization, phase interpolator, none of these things, right? It's just a flop to flop based design, okay? And that gives me the better area and power and all of that. And there was a question around power. So let's go through the key metrics here. So I'll spend a little bit of time here. It's a fairly it's a lot. It has got a lot of information here. Now, yeah, we offer the best metrics that are there, of course, and we expect with this metrics we are going to meet the compute demands for the foreseeable future. There are 3 columns here: 2D, 2.5D, 3D, right? And for the 2D, 2.5D, you will see that, you got a range of frequency, 4, 8, 12, 16, 24, 32. You got serialization, deserialization, so you can run things faster and get more bandwidth and all of that, right? Which is, and again, we don't go crazy with the frequencies there. We could, but then we would not be bump limited. We are very careful of being bump limited here. But UCI 3D it's at SOC frequency, so up to 4 gig. Now the width of each cluster is 16 for standard, 64 for advanced, and 80 for 3D. And you can, of course, have multiple sets of them to aggregate more bandwidth. These are the range of bump pitches: 100 to 130 for 2D, 25 to 55. We talked about that. 3D, we expect it to be 10 micron going down to 1 micron and possibly sub-micron into the future. But we do support 10 to 25 from a functional point of view, but you get the best benefit as the bump pitches reduce. Channel reach, 25 millimeter, 2 millimeter, this is practically 0. So face to face, face to back, back to back, all of that, and you can stack them. Now, let's look into, the bandwidth density. So these are some of the key metrics here. The bandwidth density here, it depends on the 2 things. What is the frequency of operation and what is the bump pitch? And we measure the 2 aspects of bandwidth density. One is the linear, which is the source line. If you're coming to the source line, how much bandwidth do you get per source line? Because that's going to be one limiter. The other one is, in order to deliver that bandwidth, how much area are you consuming? So that is so it's the linear and then the aerial. And you'll see that there is a range of numbers here especially for these. And these set of numbers are dependent on the frequency of operation. Again, 2D, 2.5D, I'm assuming 110 micron bump pitch and 45 micron bump pitch. So for example, you get 188 gigabytes. By the way, these are in gigabytes per second per square millimeter, not gigabits. People always ask me that question. Did you mean to say gigabits? No, it is gigabytes, capital B. So you get 188 if your frequency is 4 gigahertz. You will get 376 gigabytes per second per square millimeter if it is 8 gigahertz, and so on and so forth. At 32 gigahertz, you will get 1350, which is at more than a terabytes per second per square millimeter. It's a lot of bandwidth. Now, coming to 3D, you will see that there is, I put an NA here. Why is it NA? Well, I don't go to the source line, so I don't consume any source line. I could say infinite, but NA is a more, it's a more reasonable way of saying it, right? It's not applicable because it's a vertical connect. I don't use any source line. So here, if you look at it, this goes all the way from 4,000 or 4 terabytes per second per square millimeter at 9 micron to 300 terabytes per second per square millimeter at 1 micron. How do these compare with external interconnect? External interconnects are like PCI Express or CXL or Ethernet. Those are double-digit gigabytes per second per square millimeter. So you get, with standard and advanced, you get 1 to 2 orders of magnitude improvement. And then once you come to 3D, it's yet another 1 to 2 orders of magnitude improvement in bandwidth. I think there was a question about power, and then I believe also a question about the power dissipation, which I will get to. So power efficiency numbers, these are the peak bandwidth consumption numbers: 0.5 for standard, 0.25 for advanced 2.5D. And for 3D, we start with 0.05 at 9, and then by the time we hit a micron, we have 0.01 picojoule per bit. By the way, at these numbers, you are very similar to at par with what you would see for on die, because if you travel 2 millimeter distance, you still have to go through multiple flops, and this is basically you are evening out at this point in terms of your power consumption. And the other thing I want to point out is with vertical integration, you are moving effectively from a 2D interconnect structure to the 3D interconnect structure. So your average distance is less, your maximum distance is less for data if you're moving data around. As a result, you are going to have even better latency and even better power than if you had like a very huge, large monolithic, imaginary 2D die, for example, right? So these are the numbers. How does it compare with external interconnect? They're in the 5 to 10 picojoules per bit. So you get an order of magnitude improvement by the time you get to 2D, and yet another order of magnitude improvement once you get to 3D, right? So, which is what you would expect, because these are again very simple circuits, right? It's not that there is anything magical here. You're not doing a good job on the external interconnect. Those are much more harder interconnects to deal with because you're going through the board, you're going through a lot of discontinuities, all of that. So you need much more, advanced circuits there. We are bump limited here. We are not bump limited in the external interconnect world. We are circuit limited. The other aspect is low power entry and exit. This is important for getting linear power consumption that is proportionate to the bandwidth usage. And by that, what I mean is that if I consume 10% of the peak bandwidth, I would expect to consume 10% of the peak power, right? So it depends on how fast I can turn these circuits on or off and how much of power savings I get. So with these low power things, with the planar, you have about 0.5 to 1 nanosecond time to turn things on or off, and these are spec'd. So it's practically, you can look into what's coming in. It's 0.5 nanosecond is 1 2 gigahertz clock cycle, right? So you can look into if you have data, you send the clock, you consume the power. If you don't have any real data, you turn the clock off, you save power, right? It's about 85% power savings is what we expect on these numbers. And 3D is practical, it's zero. Basically, you just don't have the data, don't send the clock, and data go hand in hand. Reliability, we measure that in FIT, which is failure in time, and that is significantly less than 1. As long as it is, these numbers are, 10 to the power minus 10 kind of numbers. So as long as they're less than 1, they're practically zero. Just to give you an idea, any chiplet that you have, it has a FIT which will be in 3 digits kind of number, right, across the board. So interconnect FIT should be significantly less than 1, which it is. Now, so we have very compelling power efficient performance. Now let me address the question which was around, hey, how do you deliver power, especially with the 3D, and how do you dissipate power, right? So power delivery, for that we have, by the time, especially for each and every one of these, I didn't show any bump map, but you will see that there are power and ground. So you use that to deliver the power. And by the time you go to 3D, by the way, these numbers that I quote, at some point they become close to half of the bumps are power and ground bumps. So, the bandwidth has been derated based on that. So 0.1, and same way over here, okay? As far as the power dissipation is concerned, right, it's power, of course, the power delivery is concerned, you're going to have your own vias and all of that in order to deliver power for the rest of the chiplets, right, as you go through the vertical stack. And same way with the power dissipation. If you look into HBM, people are building dies, 8 high chiplets on top of a logic die, and there is talk of going to 16 and 24 tall structures. Now you have to be careful though about how much of power gets generated, so that way you are not compromising the operation of the upper layers, right? So that becomes a part of the design that the chip designer needs to comprehend. Some of the things that people are looking at is, are there other ways in which we can dissipate power independently? And then, can we have things like, for example, there is a lot of work going on around package level liquid cooling, all of those kind of things that will enable us to easily dissipate power. And those are going to be the thing. This is part of, again, there are a set of technologies available today, and we expect those technologies to significantly improve going forward. Avi, did I answer the questions that you're asking?
I hope so.
Okay.
I can.
That's fine. Otherwise they can ask me again if I missed something. So let me try to wrap up here. So, where do we go from here? By the way, we announced the UCIe formation of a consortium in March of 2022. This is sometime in fall of 2023, barely a year and a half later. You will see, our CEO basically demonstrating, and you will see this is the demo here. Interoperability. This is exchanging flits at speed for UCIe 2.5T. This is using Intel EMIB technology. So between two test chips, one of them is the Intel test chip, Pipe Creek, and the other one is a Synopsys. Intel's is in Intel process node. Synopsys was in TSMC process node, and running at speed using the Intel EMIB as the packaging technology, right? We have several, so think about the process, right? I mean, you announce the spec, companies go do their designs, and as you would expect, the IP vendors will be the first one to intercept, so that way people can take those IPs and build on top of that their products. Within a year and a half, you have people not only checking out that design in their own labs, but also they feel confident that they can package together dies coming from different sources and demonstrate interoperability. And just to, this is the early this year on the Chiplet Summit. Take a look. It's pretty much. My apologies if I missed some of the IP vendors here. I probably have, but AlphaWave, Cadence, Synopsys, all of them had their working silicon demonstrated, test silicon demonstrated on the floor. So to summarize, right? So basically, this thing is real, and it's. I've done PCI Express, I've done CXL. This is UCIe. The pace, which is a good thing to have, is a lot more than what we had, both in terms of people doing things in real silicon, as well as people coming with these demands. So whether it is, hey, I need to solve this problem holistically for chiplets, right? I mean, that basically led to 2.0, or automotive guys coming in saying, hey, I need these, everything else is there, I need this one or two extra things, right, for me to meet my needs, right? Or 3D, for example, right? I mean, those are the things that have happened, right, practically within a year of each other, right, which is at a breakneck pace we are moving. So we continue to evolve the technology. I always say that technologies like these are a journey. It's never a one-off thing. These are going to stay there for many, many generations, hopefully for many decades, and solve the problems that we need to solve in order to deliver the power efficient performance that the world needs out of us. So I'll pretty much stop here, and then let's open up for discussion. And yeah, I can stay a few minutes past the top of the hour if needed. So go ahead.
First of all, thank you very much. Exciting talk. There's one question, another question about, can you comment on scalability and test and debug a unit for complex chiplet-based systems?
Yeah, so the scalability, if I understand the question, can I comment on the scalability aspect of complex chiplets, right? So let's go back here. So if you want to do this testing, debug, all of that, So, if you look into, let's pick testing, right? I mean, some people need low bandwidth, like a JTAG pin is enough, right? I mean, if you look into the JTAG, that's basically the bandwidth level there, 5 to 100 megabit per second. That's good enough for some people. Great, right? No worries there, right? For some people, they need multiple gigabits per second worth of scan chain bandwidth, right? And the question is, how do you deliver that? The same way with the debug, by the way, right? I mean, your debug needs can be widely, it can vary wildly. And that's the reason why, if you look here, about numbers, we have allowed people to have dedicated, just a sideband pin. By the way, you can just have one sideband pin and you can connect them across these chiplets in a, whichever ring kind of a topology. And then, at some point you're going to end up with a package pin, right? Using the chiplet. But you can imagine you can have like a separate ring that goes across, right? You can just have one sideband. What is a sideband pin? A sideband pin is, it's 4 pins basically, right? So you get 800 megabits per second per direction, right? And if you have two sets of them, one ingress, one egress, right? 800 in, 800 out in each direction, right? So 800, 800. So that's basically what you get, right? 1600, 1600. And of course, in reality, you're going to get half of it because you're basically routing things through. But nevertheless, these are even by itself, right? Just the sideband for 4 pins, 800 megabit per second, it's close to a gigabit per second of bandwidth. That's a lot of bandwidth, right? Now, that may not be enough for a lot of people. As I said, some people they're not happy with megabits number. They need gigabits kind of number of bandwidth. And that's fine. In that case, you go with this. Again, I put standard here. If I put advanced, my numbers will go up significantly higher. But then I also realized that advanced I cannot pro. So I've left the advanced out here. But you can say that, hey, I want to have the advanced for the manageability and debug and only standard for testability. You have those choices. But even here, I mean, 32 gig, you are getting 512 gigabits, in terms of gigabytes. I believe that will be 64 gigabytes per second per direction, right? We allow by 8 configuration if you want to go for less. So we have a menu of choices in terms of what you can get. So it's fairly scalable. And by the way, if you need more, you can have yet another set, right? And these are not pin inefficient. These are very pin efficient interfaces. They hardly consume any source line. If you look into a by 16, your source line consumption is about a millimeter, I think, if I remember correctly. So, and this is the bandwidth number you get. So.
Vinay has 3 questions, so maybe I allow him to ask
Okay.
So, do you like to?
Hi, Debendra Sharma. Nice talk. My first question was, you mentioned for an automotive application, certain requirement or certain additional features have been added to UCI. So what are those automotive specific requirements that are catered in the UCI standard?
Sure. So actually, there is a white paper that I did in the UCI website. It's there. If you go to the UCI website, look for UCI 1.1 white paper. If you download that, I talk about that in some detail. Anyway, so from an automotive side, we looked into, what are the things that we need, right? I mean, we need things like proactively, you need to be able to figure out if things are failing. In general, we had a lot of those capabilities already built in, right? So we had mechanisms, for example, where you can, with the flits, you can inject things like a parity flit, okay? If you inject a parity flit, you will know which lanes are failing, right? And you can know their distribution. What we didn't have at that time, we had only one register that said that, hey, something, I had a recovery event, right? We didn't have like a per lane basis register. So we added just that, okay? Things like you want to margin your link. Well, you margin your link when you're link training initially. So you have a capability of measuring the eye height if applicable and eye width, right? That's the most important part. We added a register where it gets reported. And also there is a mechanism we already had a mechanism whereby you can inject, you can redo the link retraining, for example, right? So it's a set of those things. When you looked into, most of it was already there in 1.0. So there were a few things, and all we did was we just added config registers to report it.
Thank you. That was good. I'll also go through that white paper.
Yeah, go through the white paper. By the way, each of these 1.0, 1.1, and 2.0, they have white papers. And also in this talk, I point to several places where there are details available. If you're interested, you can go, like, this is like a Nature Electronics paper we did that led us, very early research we had done that led us to some of the 3D concepts. So you can take a look at those. And I believe, in several places I have put those references in there. So.
So thank you. I have another question where in one slide you mentioned about the UCI retimer to interface with the optical. The question there is, it's not very clear how that interface with the optical is, and is there any specific features which are present in the UCI to take care of this electrical to optical connection?
Sure. So this is the slide I believe you're asking me about. So what we define is, if you think about, there are different, first of all, there are different technologies, optical technologies available. And what we do is that we offer this interface. Think of it as, draw an imaginary line here. We define how this side works, right? We don't define how the optical works, because again, we are not in the business of standardizing the optical interconnect. There are multiple approaches out there. And those will exist, and the market will figure out which ones work for which usages, right? Our goal here is to define what you need to do at the chiplet level and how do you make it interoperable. So there are a few things that we realize. One of them is, for example, the optical side might take a longer time to train than an on-package interconnect. So we have defined within the spec that says that, hey, I'm dealing with an off-package retimer. So there are places where you pause in the training, right? So we added those. We also realized that once you go off the package, and this is not just optical, but for a wide variety of other types of technologies that take you off the package, could be even copper cable kind of thing, doesn't matter, right? Or there are other types of waveguide mechanisms that people are working on. So there, the bit error rate, so here our bit error rate is very stringent. There it may not match the bit error rate that you have. So what we have done is we have defined, like PCI CXL, they have their own FEC. So we have said you can use those if you want. You can come up with your own FECs, CRC mechanism that's on the other side. And, we have a physical layer based throttling mechanism that we have defined at the UCI level. So it's a physical layer based crediting mechanism that we have defined so that, you could do the translations, right? Because it's no longer a seamless bit passing thing if you need that. So those are the types of hooks we have defined. Did that answer your question?
Yes, surely. Thank you.
Yeah. Okay.
Okay, there is another question for Guy Ben Artsy. What type of attack are in scope? Side channel, etc. Maybe I extend it. Can you talk a little bit about security and the chiplet technology?
Yeah. So, a good question. So first of all, if you look into each and every one of the PCI Express, CXL, all of those, right? I mean, there's basically a DMTF is defined a set of mechanisms that all these interconnect standards are leveraging, right, in order to provide with the security enhancements. So we have a notion within UCI that there is a root of trust, which is the management director. So that's the root of trust. And it is responsible for, so you got all of your encryption, everything that you want to have. And then based on that, you want to make sure that your links are secure. So there is an elaborate mechanism that we have defined, in addition to, link encryption and all of those to make sure that the chiplets are secure.
Yeah, well, maybe final question, if you can extend a little bit about what you think that the academia can contribute to this technology?
Yeah, actually, that's a very good question. And we periodically talk about it, right, Avi? So uh, I think there are a few things that come to my mind. And as I told you earlier, that as we talk normally, these are like more of a dialogue as to what the academia can do, rather than me giving a canned answer. I'll attempt the canned answer right now, right? Because it's not enough time to do the back and forth discussion, right? I'm happy to have that separately. But so there's a lot of work that the academia does in terms of looking for, there is the, what I would call, there is a 5-year horizon, there is a 10-year horizon, and 20-year and beyond kind of horizon, right? So clearly in the more than 5-year to 20-year kind of horizon, a lot of like hybrid bonding, for example, right? I mean, is there another equivalent to that? There were questions around, hey, how do I do power dissipations, right? Are there better ways for us to do power dissipation? Some of the things that are going to be very fundamental, I believe those will come from academia, right? Industry will solve it, right? If we have to solve it, we will solve it, okay? But it's good to have a menu of choices for us to look at, right? When those become a challenge for us, right? So definitely in the areas of how does the interconnect look like? How do you do power dissipation? How do you do cooling, thermal, all of those things? On the other side, for example, how do you validate this? And how do you formally validate it, right? Something that will, be close to you, right? How do you make sure that are there things that if I'm getting things from different places, are there tools that we can have which can make that journey seamless? As you can see, right? I mean, this is basically getting close enough. For example, where it's looking like even though these are two different chips, two different process nodes or whatever, they are where the boundary is just not there anymore, right? I mean, it's no longer that well separated out by a separate set of real phi and all of those, right? And that's basically the need that we are getting to. So are there those kind of things available? The other thing is that, okay, actually this is a good one, right? As you can see, I'm making these things up, right? I mean, these have been there as streams of thought, right? What's a good is there a way for us to do a good partitioning of functionality, right? If I have something that is this functionality, I characterize it with this, right? I mean, at some point, once you partition things, right, you're basically moving the communication across, right? All of those things, right? What's a good, and then there are going to be challenges, right? Is there a good way for us to model that, right? And do. So these are some of the thoughts that I have. Of course, things like test, debug, security, all of those are going to be evolving areas. I mean, it goes without saying, right? And, we can always make things better, but some of these things that I mentioned would be good things for the academia to be involved. So again, looking forward to anyone here that is interested, it should be reaching out to people like us. So
any other questions?